Here are a couple of problems from the Stokes theorem section. So Stokes theorem, remember, is a way for us to compute line integrals, the work line integral, and specifically it is for a situation where we have a closed curve. And what it says is to do that integral, what we can do instead is do the flux of the curl, where S is any surface bounded by the curve. Any surface bound by C. So in this problem we have a cylinder, x squared plus y squared equals 9. So roughly here, that would be a cylinder of radius 3 in the z direction. So something like so. And then the plane x plus y plus z equals 1. So x plus y plus z equals 1 would be a plane that if we were just going to draw the plane, we would draw those three intercepts. And that's the piece of it that we see in the first octant. That doesn't give us a very good picture of where it intersects the cylinder, though. So you just kind of need to use your vision here and think about if you had this cylinder, like your water bottle or something, and you came and sliced it with a plane that is leaning backwards like that. And I think that you can sort of see what you would get is you've got this plane that's kind of leaning backwards, and I'm going to give you a better picture in a minute here. And if you do that, you're going to get some sort of curve that does something like this. Okay. Now, that's as neat of a picture as you need. You only need to be able to see for yourself what's going on. Okay. But if you wanted a better picture, some of the, artistic tools that you can use are the idea that we would need to know our plane cuts through here. So what we might want to know is for some of the key points on this surface, on the cylinder here, so our domain, our projection in the xy plane looks like it's going to be that circle. So what we could do is build up from that domain. We've done this before. So for instance, if I put in this point where y is 3 and x is 0, and here's x0, and x3, y0, and so on, and we put it into the equation of our plane, we'd see where these 4 points get mapped to, and that could help us draw a better picture. So for instance, when y is 3 and x is 0, I get 1 minus 3 is negative 2, so that means we would be 2 units down here, so 2 units down, like so. And when x is 3 and y is 0, again we'd be 2 units down from here, like so. When y is negative 3 and x is 0, I'd have 1 minus a minus 3, which is 4, so we'd be 4 units up over here, so like this. And same when we're above this point where x is negative 3 and y is 0, we would be up 4 units there as well. And so that gives us a little bit of an idea of where those points get mapped to. And we can maybe get, whoops, I missed that one. We can maybe get a little better idea of what's happening here. So this is the plane right there. That's the plane x plus y plus z equals 1. And the curve that we're talking about then is this black curve. So if it helps you to envision it even better, here's the computer picture of it. It's rotated a little bit. The positive x-axis for me was going this way. They're rotating it where you can see a little bit better. But then this is the curve of intersection right here. Okay, so what about that curve? The curve counterclockwise as viewed from above. So that is our positive direction. So the what Stokes' theorem tells us then is that if we want to compute the line integral about that, and we could do it directly. We could find the parametric equations that satisfy this and do it directly. But another option is to compute the curl and then do the flux of the curl. So if we compute the curl, first of all, curl of f ijk partial x, y, and z, x squared z, xy squared, and z squared. Partial y here is 0, partial z there is 0. I component, j component I mean. Partial x here is 0 minus partial z here is x squared. We're in the j position, so we take the opposite. Okay, partial x is y squared minus partial y is 0. So y squared. So we need the flux of this curl vector field. So we need to figure out what surface we're going to use. We can use any surface bound by this curve. And so this piece of the plane is going to be the surface that we want. So this is our surface. So our surface, S, is given by that plane. And I'm going to write it in the form z equals 1 minus x minus y. That is, I'm thinking of z as a function of x and y. This can be represented in any of the three orientations. But I can see the projection in the xy plane, so it makes sense, makes best sense to treat z as my dependent variable. So how do we do this? We get everything on one side, and that's what we call our g, if you're using the notation that I like for the shortcut. And the gradient of g is 1, 1, 1. We wanted a 1 in the z position because z is the dependent variable. Do we want an upward normal here or a downward? Upward or downward? The curve has positive orientation, and so the surface needs to have positive orientation as well. So this is what we want. Then we take the dot product of the curl, and the gradient there, keeping in mind that everything needs to be in terms of x and y. This is already in terms of x and y. But had there been a z in here somewhere, we would have to have put this in for any z's. Okay, and so then the line integral will be the double integral. Again, how do we do flux integrals? It's the double integral of that vector field dotted with the gradient of g dA. And so that dot product with the curl and the gradient is 0 minus x squared plus y squared. I made a mistake. Right here, the j component, that's going to be 0 minus x squared, and in the minus position, so that's positive. And so this is positive down here. Okay, and so the projection into the xy plane, you can see here, is that circle of radius 3. D is into the xy plane. circle of radius 3, so polar, 0 to 3, 0 to 2 pi, x squared plus y squared is r squared, and then r d theta. All right, you might try, just for practice, to see if you could do this one directly. If you were going to do this one directly, you'd have to parameterize that curve. And so to parameterize that curve, what we'd want to do is x squared plus y squared is 9. That would take care of what x and y are doing going around that circle, that cylinder. But then to get z, well, z has to be in the plane, so 1 minus x minus y. So that would be 1 minus 3 cosine theta minus 3 sine theta. So if you were going to try to do this directly, this would be your parameterization for the curve. Theta would go from 0 to 2 pi, so once around. By the way, you could make those t's if you wanted to. Yeah, we're used to those being t's. But then to do that directly, then you would just put these in for your x and y's and z's here, which I can see it looks like it's going to be pretty messy with cosine squareds and the like. And then you dot that by r prime. Okay, so looks like you can do it okay, but it looks like it's going to be a little bit messy of an integral. All right. Okay, so in this one we have z equals x squared plus y squared. That's a cone. The part where z goes from 0 to 4, so 0 to 4 is here. And so that's going to be like so. All right, so something is missing in my instructions. Hang on. Okay, it says to verify Stokes' theorem. And so when they ask us to do that, it means to do the integral directly and do the integral using Stokes' theorem. And make sure you get the same thing. And I often do something like that as well. I don't think that they asked the question very well here because they didn't tell us what curve. That's interesting. So this is the surface they want us to use here, the cone. And so then we would need to find a curve bound by the cone. So it's asked a little bit backwards. Usually we're given a curve bound by the cone and we have to find the surface. So a little strange way to ask that. But if I were to find this curve C in the positive direction, so counterclockwise, then it is a curve that bounds this surface here, which is the surface that they wanted us to use. So that's what we're going to do. We're going to apply Stokes' theorem. We're going to look at the work integral about this blue curve, and then separately we'll look at the flux integral of the curl for the red surface and see if we get the same thing. Okay, so let's do the curve first. As far as the curve goes, it is a circle, and it is where z equals 4, I have x squared plus y squared equals 4 squared, or 16. So it is a circle of radius 4 there. This is a circle of radius 4. Parameterizing that curve, we get x equals 4 cosine t, y equals 4 sine t. That'll get me the circle, and then we are in the plane z equals 4. and once around there. So putting that into our f is minus y, x, and negative 2. So I'm just grabbing my f here, putting in my y and my x. We also need r prime. So r prime would be the derivative here. So negative 4 sine t, 4 cosine t, and 0. So for line integral, directly, recall, it's going to be the integral of f dotted with r prime. And so that's going to be here 0 to 2 pi, and then this dot product is 16 sine squared plus 16 cosine squared. That's 16 plus 0 dt, and so that's 32 pi if I integrate that. Okay, so that is directly for the curve oriented this way in the positive direction. Now my other way is to look at the flux of the curl. So if I want to do the flux of the curl, shorthand notation, but the shortcut that we use, is the curl dotted with the gradient of capital G, chosen in that particular way, over the projection. So in this case, our surface that we're using is that red surface. We have to be a little bit careful about this because here's the red surface. X squared plus y squared. Z squared equals x squared plus y squared. We have to solve for z first. So solve for z first. Remember, we have to get a coefficient of 1 on our z. So z would be plus or minus, but we are just talking about the top of the cone. Then get everything on one side. Now this is your g. And so we take the gradient of g, and we get partial with respect to x. That's going to be a minus x over that square root. Partial with respect to y. And partial with respect to z is 1, and I wanted 1 in the z position because z is the dependent variable. Okay, now there's actually a twist in this problem, and that is here we're asked for downward orientation. Now the way Stokes' theorem is stated in your book, it assumes positive orientation of the curve combined with positive orientation of the surface. And now they're asking me for downward orientation of the surface. Okay, so what is that going to cause to happen? Well, if positive orientation of the curve matches positive orientation here, then if what I want is negative orientation, that's going to give me the opposite of the answer. Then I'm going to need the opposite of the answer for the curve. And taking the opposite of answer for the curve is the same way as changing the direction. Okay, so let me try explaining this another way. The way your book says Stokes' theorem, it says always use positive surface, positive curve. But I mentioned when we were discussing it that you don't have to have them both positive, you just have to have them both match. So if here they're asking us for downward orientation, then what we could have done is just said, okay, you want downward orientation, then this has to be negative orientation. They just have to match. So what I'm talking about here is we're going to have a difference in sign. that we have to deal with, and you can deal with it anywhere along the way. So let me just show you what I mean. Let me just keep this the way it is, and let me do this flux, but I'm going to choose the downward orientation because I see they asked for downward, so I'm going to right here at this point choose downward. Downward, downward was asked. So I'm going to choose minus the gradient of g, which is going to be a positive, and a positive, and a negative. Okay, I need the curl of f. The curl of f. I'll let you compute the curl of f on your own there. You're going to get 0, 0, 2. So now we need to take the dot product of these two and we would get negative 2. And so back up here then, our integral is going to become negative 2 dA, and the d is the projection into the xy plane, whoops, I missed, which is a circle of radius 4. So we can just do this using the area interpretation. This is negative 2 times the area of that circle of radius 4, which is pi times 4 squared, so negative 32 pi. Okay, now these should match. If I'm going to use this to compute this, I should get the same thing. So what's wrong here is that this used a negative orientation because they wanted me to use negative orientation. Then this should use negative orientation to match. All right? Or go ahead and do the positive here and then take the negative of the answer at the end. But you just have to account for that downward somewhere. So the way that I like to do it, okay, your book just kind of says make everything positive and take a negative at the end sort of thing. I like to do it by thinking ahead of time. If this is asking me for a negative orientation on my surface, then I'm going to parameterize this with a negative orientation for my curve. All right, now I didn't. I parameterized it with the positive orientation. So then what I would have to do if I wanted the opposite direction is just to take the opposite here. So I could have parameterized it going that way and done it directly that way, or I can parameterize it going this way and take the opposite, because remember, if you change the direction of your travel, your work will become the opposite of what it was. And so in the end here, what we have is that both of these are negative 32 pi. All right, this is another one that's asking us to verify Stokes' theorem. And so we have S is the hemisphere where y is greater than or equal to 0. Okay, I almost went right past that. So we're talking about the right half of a sphere. Oriented in the direction of the positive y-axis. So this is the surface. This is the surface that they want me to use. So the curve that they're implying is this one, which my picture doesn't look so great here. I guess theoretically this would be behind. This is behind here, and the blue surface comes like that. Okay, it's the right half sphere. So the curve the curve, is the unit circle, but it is in the unit circle in the xz plane. Now before I parameterize that, I need to think about what the positive direction for that curve will be. So in this case, y is playing z's role, and so on. So the way that we talked about the direction of travel is if I were to walk along this curve with my head pointing in the direction of the positive surface, I would need the surface on my left. The other way we talked about it is we said if we look down from above. Well, now we're looking at everything from y's point of view. So if we look down from the y-axis, we need things to be counterclockwise. So that's from the positive z to the positive x-axis. So that means we actually need to parameterize my curve going this way, which is the opposite of the way that we are normally used to doing it. So that's a little tricky. So I need to parameterize that going around this way. Now there's lots of ways you can go about that. One would be we can go ahead and do like we're used to with cosine and sine, but it would be minus sine. Because if I put in t equals 0, I'm at this point 1, 0. Whoops, this should be a z. Okay, so I'm here at 1, 0 when t equals 0. And as t increases, so like when t goes to pi over 2, x will go to 0, but y will go to minus sine of pi over 2. Y is going down this way. So this parameterization will have us go the way that we want here. We need a y in here. Y is 0. We're on the xz plane here. So that's our curve. We put it into f. So f is yzx. So yzx. So 0 minus sine t, cosine t, and r prime is the derivative here. So minus sine 0 minus cosine. And so that dot product is just minus cosine squared from 0 to 2 pi. So that's negative 1/2 t minus 1/4 sine of 2t. So that's going to be minus pi. So that's what we get if we do it directly. If instead we use the flux of the curl, then we would be using I actually say flux of the curl in my head when I write this down. And so this is the double integral of the curl dotted with the gradient of g, the surface there, dA over d. Okay, so this time, this right-hand surface, this is a function only from y's point of view. So this makes most sense to think of our surface as y is 1 minus x squared minus z squared. So g of x and z. So this, we're going to be doing this one from the other point of view. Everything's going to be in terms of x and z. So this is good practice. So what do we need? We need the curl and we need the gradient of g. So to get the gradient of g, first we have to see what capital G is. We get everything on one side. And this is what we call capital G. So the gradient of this is going to be x over the square root of 1 minus x squared minus z squared. Partial with respect to y is 1. Partial with respect to z is z over radical 1 minus x squared minus z squared. The curl of f is negative 1, negative 1, negative 1. I'll leave that for you to compute. And so the dot product of these two, I guess I didn't stop and think right here. The 1 is in the y position, which makes sense because y is the dependent variable. This is supposed to be oriented positively, so oriented positive y direction. So yes, that is what we want. Now we take the dot product of these two and we get a lot. Negative x over that radical minus 1 and minus z over that radical. And so we're going to need then to find the double integral of, I can factor negative all the way out there, I suppose, huh? And I get x plus z over 1 minus x squared minus z squared, and then plus 1 dA. And my d is the projection in the, it's right here, xz plane, which is a circle of radius 1. Okay, so one thing I would probably do, let me just do this first. X plus z over radical 1 minus x squared minus z squared minus dA. I'm going to break them apart because for this part I can just use the area of that circle. So the area of that circle, pi r squared, the area is pi. So this part right here is just minus pi. So I can take care of that right away. This part, I suppose I would go polar. And I'm just looking 2 steps ahead here. And it's going to be a lot. We're going to have a 1 minus r squared here. We're going to have r and another r. So we're going to have r squareds on the top, which suggests trig substitution. If I did rectangular, then if I let u be all of this, then du dz would be negative 2z. That would pick up that one. Yeah, actually, I think this, unless I've missed something, this is a pretty involved integral this way. So I don't think I'm going to work that one. I'm not going to give you one that is that complicated to work. I will look at it after I'm done recording and see if I've missed something that would have made it, something neater here. Maybe I've got something wrong in the computation. But what we should get is the same thing. By the way, if I asked you to do a problem both ways, like this, and you can't get this and you fudge the answer to match, don't do that. All right? Because sometimes what happens is your answer doesn't match. It's telling you that you have a mistake. Go catch it. All right. This particular problem, so the topic that we didn't get to, that I wanted to, is parametric surfaces. So parametric surfaces make spheres and cylinders easier to deal with. Also cones. From some points of view, when you have a surface that is easier to not, when you have a surface that can't easily be expressed as a function, then oftentimes parametric surfaces is helpful. Just a note, I did look at this integral, and whether you go rectangular or polar, it will involve trig substitution. Now, you should be able to do trig substitution. So you might try that. The easiest way to do this one is polar and a trig sub. But I wouldn't put one of those on your test. Okay, so this one is asking us to evaluate this, which remember, this is just the work line integral in differential form. If you prefer, you can think of it as f equals y plus sine x, z squared plus cosine y, and x cubed. And then this is our r. So whether you like to put in the y and the x and then dx dt here, dy dt, dz dt, or you treat it as a vector, same thing, same computation, all that. When they're asking us to compute this then, it's the same as asking us to compute that. I tend to prefer this notation. I've just gotten used to it, but either way is fine. All right, so this curve is not one I know offhand, and so I'm ignoring the hint here for a minute. And probably, you know, if I were to draw that, I mean, we should be able to draw that. That would be a problem in and of itself. We learned how to do these. We eliminate the parameter and so on. Maybe I should do that. Maybe that would be a good review. But first, let me focus on the problem at hand. If I didn't know offhand how to draw that, and I know that it's some sort of complicated thing, and they didn't tell me some surface, because I'm not reading the hint yet, then my first try probably would say, hey, maybe I'll just do this directly. If I do this directly, then I need to put f in terms of t. So here's my x and y and z, so I'm going to plug in for y, I'm going to put in for x. Okay, so my f is going to be y, which is cosine of t, plus sine of x. X is the sine of t. And then z squared, that's sine squared of 2t, plus cosine of y. Y is cosine of t, so cosine of t. And then my third component is x cubed, so sine cubed of t. So I'm already a little worried. Then I need r prime. So that would be cosine t minus sine t, 2 cosine 2t. And then I start picturing that dot product. And it looks like it, well, you know what, it's not impossible. Let me just write it out. It's going to be cosine squared of t plus cosine of t times the sine of t minus the sine of t times the sine squared of 2t, if I'm not making a mistake here, minus the sine of t times the cosine of t, and then sine cubed, 2 cosine 2t sine cubed of t, maybe, okay? And so then I would integrate this from 0 to 2 pi. And it's doable. Even one like this, the sine of t, when it starts looking like, are you kidding me? But if u is sine of t, du is cosine of t, and this integral just becomes sine of u. So that's not bad. This one looks pretty bad. But sine of 2t is 2 sine t cosine t, and then you square that, multiply it by a sine of t, and you've just got powers of sine and cosine. That's not too bad. This one, let u be cosine. Du is minus sine, so you get a cosine u. That one's not too bad. This one is going to be a little worse. Nope, not. Just put in the identity, and that one's not too bad. So you could do that. And if you want to give it a try and work it out just to see, go ahead. But it looks kind of like a long way to go. And so probably here's what I would do if I wasn't reading the instructions or anything. I'd probably say, wow, I don't think I want to do that directly. Maybe it's conservative. Okay, maybe it's conservative. If it is, this is a closed path because 0 to 2 pi, that's a whole period. The period here is pi, so 2 pi 2 times around, but this is a closed curve. So if f is conservative, then I get 0, and that's great. So I'm going to see if f is conservative. So I'm going to look at the curl of f. Partial x, I'm going to need more room, partial y, partial z, y plus sine of x, okay, can't zoom. I changed the rules. Okay, where'd it go though? Y plus sine of x, z squared plus cosine of y, z squared plus cosine of y, and x cubed. So curl. Partial y, 0, partial z, 2z. Partial x is 3x squared minus 0. So 3x squared, but in the j position, so negative. K, partial x is 0, partial y is 1, so minus 1. So f is not conservative. I could tell that as soon as this wasn't 0. They have to all be 0. So f is not conservative. So that's too bad. So what other techniques do I have? Well, I mentioned that C is closed. So I could use Stokes, but here's the tricky part. What surface am I going to use? I know they gave me a hint, but I try to ignore hints until I need them. Okay. What surface would I use? So all I know is that this curve is some sort of curve here. I don't know if it's like the edge of a paraboloid or what. So this is where, without looking at the hint, this is where I would actually have to go back and do a little bit of reviewing about how I would draw this. So I'm going to do that here. If you don't want to take the time to review this part, then you can fast forward, but it'll help for the final as well. So how do we sketch? Our process for sketching these curves. So my curve is, r is sine of t, so x is sine of t, y is cosine of t, and z is sine of 2t. And I think we actually sketched this curve back in chapter 13, but I just want to remind you of the process. So the process was we took a pair of equations, perhaps, and we eliminated the parameter. So for instance, I might have said, look, let me eliminate the parameter there. I get x squared plus y squared equals 1, which means my curve would lie on the surface where x squared plus y squared is 1. Remember the roll of paper towels I said? So my curve is going around and around here. It's going around and around. We talked about in 2 dimensions that this would be a circle and we would be going around that way. So we are going around this way, coming over the front, going to the back, and we're going around and around. And then what we did back then is we thought, okay, my curve goes around and around. I know how x and y relate to each other, but then let's bring z into the picture. And so what we would have done is something like, well, z goes up and down between -1 and 1, which means as my curve goes around and around, it's also bouncing up between -1 and 1. So it's like, you're going around a merry-go-round and the horse is going up and down. So that's sort of the thought process that we would have done. And then if we still don't have a really good idea, then what we might have done is to take another pair and eliminate the parameter and get another surface. Okay, get another surface on which the curve lies. And so this is where their hint comes in. Suppose I took this and I said z equals sine of 2t, which is 2 times the sine of t times the cosine of t. But in eliminating the parameter, sine of t is x and cosine of t is y. So that is some surface that joins, whoops, I got a 2 there, 2xy. So I don't really know what this looks like, but it is apparently a surface on which our curve lies. Now I graphed it just to get a better feel for it if it helps convince you. This is the surface z equals 2xy, and if I took this cylinder and I put it on here as well, so we'd have something like this going around and up and down, then what our curve looks like is it's going down and up here and down in the back and up and around. Okay, not a very good picture. But the point is that it is the boundary of part of that blue surface. And that blue surface has the equation z equals 2xy. So that might have been hard to come up with without the hint. Well, at least picturing it without the graph and all that. But this is how we can find surfaces on which our curve lies. So if you need to use Stokes' theorem and you need to find a surface on which your curve lies, you can do the same sort of thing we did to draw them. So then that means to do this problem using Stokes' theorem, we're going to use the surface z equals 2xy. Okay, so that's in the form f of x and y, or g, I've been calling it. So z minus 2xy equals 0. That's our capital G. And so the gradient of g, minus 2y minus 2x and 1. Okay? And the curl, let's see, we've got the curl here. So we just need to take the dot product, put this surface in here. So let me put in for z. Whoop. Negative 2z. Z is 2xy. Minus 3x squared minus 1. All right, so we're just going to dot these two and then do the double integral over the unit circle. Now there is a question about direction here. There's a question about direction. This curve was given to me this way, sine, cosine, cosine of 2t. And actually, you know what, I made a mistake over here when I said it was going this way. I'm so used to it being cosine, sine. But back up over here. If I put in 0, x is 0, y is 1, and as t increases, what does x do? As t increases from 0, the sine function increases. So that means as t increases, x increases, which means we're actually going around the circle this way. We're going around this way. This way. So that's clockwise if we look from above. And so that's the negative direction for a curve. That's the negative direction. And so for Stokes' theorem, we can handle that a couple ways. For Stokes' theorem, then, we would either find the work around the opposite of this curve using this positive orientation, or the way I like to do it is just negative orientation for curve. I want negative orientation for surface. So negative orientation for curve, so I want negative orientation here. So you just have to make the orientations match. So I want minus gradient of g, which is 2x, 2y, negative 1. So then we just dot those. So we're going to take the curl and we're going to dot it with opposite of the gradient of g. So we're dotting, I always have to kind of really focus what I'm dotting. I'm dotting that with that. So 2x times negative 4xy, that's negative 8x squared y. Whoops. And then 3x squared times negative 3x squared is negative 9x to the fourth plus 1. Projection is that unit circle. Okay. So polar, probably, maybe rectangular. It looks kind of like a mess. I mean, it looks like some work there. I'll leave that for you. I hope that helps. We didn't get a chance to practice enough of the Stokes theorems problems, but hopefully this will help you to be able to do some of those problems. Take a look at, for instance, the sample test. If you look at the sample test 4 from my regular semesters, instead of your sample test 4, it will have some more of these practice problems on it. Okay, and so will the sample final.